Welcome everyone. This is the session 3 from the playlist of oscillations, and the topic is simple harmonic motions, and this is the session which is in continuation of the session number 2. So the generalized equation for the displacement of a particle which is executing simple harmonic motion is given by y is equal to a sine omega t plus phi, or y is also equal to a cos omega t plus phi. So the generalized equation for the displacement of a particle executing simple harmonic motion can be expressed in both these two ways. So here A is what? A is the amplitude of this simple harmonic motion. Phi is the initial phase, or it is also known by the another term, that is phase angle. And omega t plus phi is the phase of the particle at any instant of time, say t. The second important point is the two particles which are executing simple harmonic motion, they are in the same phase if the phase difference between them is an even multiple of pi. Here n is equal to 0, 1, 2, 3 and so on. And the two particles which are executing the simple harmonic motion, they are in the opposite phase if the phase difference between them is an odd multiple of pi, that is 2n plus 1 multiplied by pi, where n is equal to 0, 1, 2, 3. So these are the three important points in reference to the displacement of the particle which is executing simple harmonic motion. So these are the two equations. Y is the displacement of the particle, and A is the amplitude of the simple harmonic motion. Omega here, omega is the angular frequency or the angular velocity, which is given by 2 pi upon t, where t is the time period. So this is a short description about the generalized equation of the particle, the generalized equation for the displacement of the particle executing simple harmonic motion, and a very short description about the two particles which are in phase or which are in opposite phase. So if they are in phase, then the phase difference is an even multiple of pi, and if they are in opposite phase, then the phase difference is equal to 2n plus 1 into pi, which is an, or you can say that it is an odd multiple of pi. So now we will now discuss here about the phase difference of the two particles which are executing the simple harmonic motion. So now let us consider one particle. The displacement of this particle is denoted here as y1. Let us consider the amplitude as a sine omega t plus phi 1, where phi 1 is the phase angle or the initial phase. And let us consider another particle which is executing the simple harmonic motion. Let us say it is a sine omega t plus phi 2. So the phase difference, that is delta phi, which will be equal to this omega t plus phi 2 minus omega t plus phi 1. So this is equal to phi 2 minus phi 1. Now phi 2 minus phi 1 will be equal to 2n pi if they are in the same phase. This is the first point. And phi 2 minus phi 1, this will be equal to 2n plus 1 pi if they are in the opposite phase. They are in the opposite phase, and here n is equal to 0, 1, 2, 3, 4 and so on. So So this was a brief this description about the displacement of the particle which is executing simple harmonic motion, and what will be the phase difference between the two particles which is executing simple harmonic motion if they are in the same phase and they are in the opposite phase. Now the next important point is that we will now derive the equation for the velocity of the particle, which is velocity and the acceleration of the particle which is executing simple harmonic motion. So since we know that y is equal to a sine omega t plus phi, so this is the displacement of a particle which is executing simple harmonic motion. So now if I differentiate this equation with respect to t, the dy by dt will be equal to what? A is a constant. Now sine omega t plus phi, so if I differentiate it with respect to t, I will be getting a omega cos omega t, or cos omega t plus phi. Now we know that sine square cos square theta plus sine square theta is equal to 1. So from here, from this equation, you can see that sine omega t plus phi is equal to y upon a. So what I will be doing is, I will be substituting the value of theta as omega t plus phi, and I will be getting that cos square omega t plus phi will be equal to 1 minus sine square omega t plus phi. So sine square omega t plus phi will be equal to y square upon a square. So we can say that cos square omega t plus phi will be equal to a square minus y square upon a square. So now I will be substituting this value in this equation. So what I will be getting, that is the velocity of the particle executing simple harmonic motion at any instant of time. This will be equal to a omega. Now cos square omega t plus phi is equal to a square minus y square upon a square. So cos omega t plus phi will be equal to under root a square minus y square divided by a. Because in this denominator we have got a square, so the under root of a square will be equal to a, and this a and a will get cancelled out. I will be getting the equation as omega a square minus y square. So this is the velocity of the particle at any moment of time which is executing the simple harmonic motion, and this is equal to omega under root a square minus y square. Now this the third important thing is the acceleration of the particle which is executing the simple harmonic motion. So the acceleration can be found by differentiating this equation, this one, once again, that is the second time. So if I differentiate this equation again with respect to t, then d square y upon dt square will be equal to a omega square minus sine omega t plus phi, because the differentiation of this of cos, if y is equal to cos x, then dy upon dx is equal to minus sin x. So using this formula, we will be getting the value of the second differentiation, that is d square y upon dt square as minus a because the dy by this will be equal to minus a omega square and sine omega t plus phi. Because if y is equal to cos x, then dy by dx of cos x will be equal to minus sin x. So here we will be getting the minus sign, and finally we will be getting d square y upon dt square is equal to minus a omega square sine omega t plus phi. And now this can be written as sine omega t plus phi is what? This is equal to y upon a from this equation. So I will be substituting the value of this sine omega t of omega t plus phi as y upon a. So this is equal to minus omega square y, or we can say that d square y upon dt square plus omega square y is equal to 0. Now this is the acceleration of the particle at any moment of time. Okay, and sorry, this is the acceleration of the particle which is equal to minus omega square y. So here you can see that now omega is what? Omega is equal to 2 pi upon t. And what is y? Y is the displacement of the particle at any moment of time. So from this equation, I can write this equation as in this form also, that is d square y upon dt square plus omega square y is equal to 0. And this is the equation of the particle executing the simple harmonic motion, that is any particle which is executing the simple harmonic motion will have means if I differentiate let us say if I have the equation of a particle which is executing the simple harmonic motion in the form of if I have a displacement equation, that is the displacement of a particle which is executing simple harmonic motion, then if I differentiate it 2 times, that is the second differentiation should be if I get the second differentiation in this form, then we can say that particle is executing the simple harmonic motion. So in the next session I will be coming up with a couple of questions which will be based on what we have studied in this session, that is the simple harmonic motion. And so till then, have a nice day. Bye.